Today we're going to start by reviewing motion in one dimension. So if we're talking about motion in one dimension, you may recall that we worked with motion diagrams. And a motion diagram looks something like this. So I have in orange here my x-axis, and along that x-axis I have different points labeled. So this is x is -1 meter, this is x is 0 meters, 1 meter, 2 meter, 3 meters, etc. And my particle, or my object, is going to be located at different points in space at different times. So at t is 0 seconds, let's assume all my times are going to be in seconds. At t equals 0 seconds, we're at a position -1 meter. At 1 second, we're at 0 meters. 2 seconds, we're at 1 meter, etc., etc. So we can build up a motion diagram like this. And we can do this either from data or using data, and either from the data I can get the motion diagram, or from the motion diagram I can get the data. And we can just write down, well, at t is 0 seconds, I'm at -1 meter, t is 1 second, I'm at 0 meters, all the way down the line, etc., etc. And just as I made my motion diagram, just as I made my two data columns over there, I can also represent that information graphically. So if I'm plotting time on my x-axis and position on my y-axis, I can write down these different data points on this graph. I can say at time 0 and position -1, let's say here's time 0, here's position -1, so I'll start right here. Let's say that's time 1, 2, 3, 4. At t is 1 second, I'm at 0 meters. Here's 0 meters, here's 1 meter, 2 meters, 3 meters, so I'm here. At 2 seconds, I'm at 1 meter. Here's 1 meter, so we're just going to go up to here. 3 seconds, I'm at 2 meters. And at 4 seconds, I'm at 3 meters. So we can see that this is starting to trace out a nice straight line. It would be a straight line if I could get my data written in correctly. There we go. Should be a nice straight line. Now, we're going to need these three tools, motion diagrams, making data columns, and making graphs. And working with them is going to be, working with them in 2 dimensions is going to be very similar to working with them in 1 dimension, except now we're going to have to add another coordinate here. So in addition to x, we're also going to have to deal with a y coordinate. Now we're going to consider motion in 2 dimensions. And as I said earlier, motion in 2 dimensions is the same as motion in 1 dimension, but we just have to work with one more variable. So let's start by looking at a motion diagram. So we have here some points, and now, rather than just looking at motion along the x direction, I have to look at motion along the x direction and along the y direction. We can see, if I look at these points, I have a point, let's say this is at t is 0 seconds. We're at -1 meter. At t is 1 second, -1 meter in the x direction, but 0 meters in the y direction. At 1 second, we're at 0 meters in the x direction, but we're up 2 meters in the y direction. And then I can continue down the line. 2 seconds, we are up 3 meters in the y direction, but only 1 meter in the x direction. At 3 seconds, we're over 2 meters in the x direction, up 2 meters in the y direction. And at 4 seconds, we're over 3 meters in the x direction, but up a height 0 in the y direction. Just as with 1 dimension, we can write this down, we can write this information down in a table, in a data table that looks like this. And it's going to be the same thing that we did in one dimension, except now we have one more data column. So we're looking at times from t equals 0, make that a better t so it doesn't quite look like an x. We're going to be looking at times from 0 to 4, so I'm just going to write these down. 0, 1, 2, 3, 4, all the way up to 4 seconds. Let's see, I start at -1 meters on the x, then we go to 0 meters on the x-axis. Time 2, we're at 1 meter on the x-axis, 2 meters, 3 meters. So I can just write that down in my data table. At 0 seconds, we're over -1 meters. 1 second, we're at 0 meters, 1 meter, 2 meters, 3 meters, down the line. If I look in the y direction, first we start at 0 meters, right on the y-axis. Then we're at 2 meters. Then we're at 2 seconds, we're at a height of 3 meters. And then it starts to go down again. At 3 seconds, these are all seconds. I'll just put the seconds in here so that's explicit. At 3 seconds, we're at up a height 2 meters. At 4 seconds, we're back to a height of 0 meters. So that starts at a height of 0, goes up to 2, then goes up to a height of 3, then 2, then back to 0. So we can record that information either as a motion diagram or in a data table. Just as we could do motion diagrams and data tables in 1 or 2 dimensions, we can also make graphs in 1 or 2 dimensions. So using my data table from before, I can set up a graph that plots x versus time, x in meters, time in seconds. And I can set up a graph that plots y versus time. Again, y in meters, time in seconds. If I look at my data table, I can see, and then I actually have to make my time axis a little bit higher here so I can fit it all in. At time 0, so right on this axis, I have an x value of -1 meter. We have -1 meter, 1 meter, 2 meters, 3 meters, and then I just go up 1 for every second. So after 1 second, I'm at 0 meters. After another second, I'm at 1 meter. After 3 seconds, I'm at 2 meters. After 4 seconds, I am at 3 meters, just as I can see from my data table. Much like our one-dimensional graph, this is just going to give a straight line. I can do the same thing with the y-coordinates. Just as I looked at the x-coordinates to get the values for this graph, I can look at the y-coordinates to get the values for the other graph. So let's see, y goes from 0 to 3. 0, 1, 2, 3, 1, 2, 3. At t is 0 seconds, we're at 0 meters. That's right there. At 1 second, we are up 2 meters in the y direction. So right there. At 1 second. 2 seconds, we're up 3 meters. 3 seconds, we're up 2 meters. And then finally at 4 seconds, we're down to 0 meters. And we can see that this graph happens to have kind of a curving shape, which I can draw like this. So just like motion in one dimension, we can do motion diagrams, we can make data tables, and we can make graphs. The only difference is that now we have to do it twice, once for the x direction, once for the y direction. Suppose I want to specify the position of an object in 2 dimensions. Well, it turns out that's a little bit more complicated than specifying an object's position if it's only in 1 dimension. The reason being is that I have to specify 2 coordinates, both the x-coordinate and the y-coordinate. So for example, if I'm looking at where we are from our original data, time 0, here's the origin of my coordinate axes. That's where x is 0 and y is 0. Well, I can draw an arrow to that point from the origin. So this is where our object is at time 0. It's at a coordinate x is -1, but y is 0. Similarly, I can draw an arrow to where it is after 1 second, which would be right about there. It's at a position. X is 0, y is 2. Label my y positions here. This is +3, this is 2, this is 1. Similarly, I can keep going. I can specify where my object is at time 2. It's over 1 meter and up a height 3 meters. At time 3, we're over 2 meters and up 2 meters. At time 4, we're over 3 meters and up 0 meters. All of those arrows are what we call position vectors. And a vector is a way of representing where an object is if you're dealing with a space that's bigger than 1 dimension. So we're going to define vectors this way. Vectors are mathematical objects that have a pretty straightforward definition. So before, when I specified an object's position, I just told you how far away it was from the origin. All I did was give you a number. It's 2 meters away from the origin. A number and a unit. Now we're going to specify a vector this way. It's got a number, which is also known as a magnitude. It tells me how big the vector is. But it also has a direction. So, for example, if I look at these vectors, I would say, well, this vector has a length 3 meters. The vector to this point has a length of 3 meters because it goes from 0 to 3 meters. So 3 meters would be its magnitude. And it's pointing along the x direction. So it's got that magnitude, but I also have to say it's pointing along the x direction. So I could have had another vector that had a length of 3 meters. Here's a length of 3 meters, but that's not pointing in the same direction. So that's not the same vector. Similarly, I could have a vector that's 1 meter long, pointed in the x direction. That would not be the same vector as this 3 meter vector because the magnitudes are different. So to define a vector, it needs a magnitude and a direction. And to get the same vector, it needs both the same magnitude and the same direction. There are several ways to describe vectors mathematically. To start with, we're going to write our vectors in component form. So I chose a particular time here. So 2 seconds from the information I gave you before. Our object was at a position 1 meter away from the origin in the x direction and 3 meters away from the origin in the y direction. We're going to continue with, we're going to look at that point in particular and use that to write a position vector. So a position vector is a vector that describes the position of an object. And right now our object is over 1 meter in the x direction and up 3 meters in the y direction. So how would we write that? Well, we can write that very simply. We're going to write our position vector. I'm going to call it r. So we would say the position of the object is given by vector r. Here, I'm using a lowercase r with an arrow on top. The arrow simply means that this object is a vector. So it means I have to give a magnitude and a direction. Or equivalently, we can also write it in component form. So here's how we write them. We can say that my object is over 1 in the x direction. This x, notice that it is not a variable x. I can tell it's not a variable x because it has that little hat on it. The hat means it's a unit vector in the x direction. What's a unit vector? A unit vector is just a vector that tells me the direction. It has a magnitude of 1. So its magnitude doesn't matter, but it tells me that we have to be moving in the x direction. So I can say my object, at 2 seconds, is at a distance 1 meter in the x direction. Then we could say plus 3 meters in the y direction. So just as I used x with a little hat on it, I can also use y with a little hat on it to represent motion in the y direction. So I have my r vector equals 1 x hat plus 3 y hat. What does that mean in practical terms? It means, well, go over 1 in the x direction, then go up 3 in the y direction, and that tells you where you are. There are other ways of writing this, depending on which book you use. If you go into different fields, some branches of physics are going to use slightly different notations. So just to warn you what some of these notations are, sometimes you'll write it this way: 1 in the I hat direction. So it's the lowercase letter I. The reason they do this is they don't want people to get confused with x. Sometimes x is a variable, so rather than worry about that, they use the letter I instead. So you'd say in the I direction, and instead of x and y, you'd use I and j. But it means the same thing. It just means over 1 in the x direction, up 3 in the y direction. However, the notation I am probably going to use in class is more of a shorthand. Since component form always means you're writing a collection of numbers. So if we're in 2 dimensions, I need an x and a y component. If I'm in 3 dimensions, I would need an x, a y, and a z component. But as a shorthand, rather than writing these unit vectors, sometimes we just write it in brackets. We say angle bracket 1, comma 3, close angle bracket. It just tells me I'm over 1 and up 3 in the x and y directions, respectively. Just to emphasize some bits of notation, we would refer to the 1 and the 3 as the x and y components of the vector. So we can break a vector into its individual components. So how far does the vector move in the x direction? How far does it move in the y direction? So these things individually are called the components of the vector. Also, as I mentioned earlier, the x hat and the y hat are known as unit vectors. Again, these are vectors that have a length of 1, so we don't care so much about their length, but they do tell us what direction the vector is pointing in. And if I look at something that's an x hat, I know that's a unit vector in the x direction. And if I look at something that's written as a y hat, that is a unit vector in the y direction. We began this section by saying a vector is defined by its magnitude and its direction. And then we went on to say that we can write that equivalently as 2 components, an x component and a y component. Well, if that's true, we should be able to relate the magnitude and the direction to the x and y components. And that's what we're going to do now. So I want to figure out the magnitude of this vector r. And I can do that in terms of its x and its y components. I can do that pretty easily because I have here, because my components were perpendicular to each other, the x and y were perpendicular to each other, we have a right triangle. And right triangles can be used to, or I should say, you can find the hypotenuse of a right triangle using something called the Pythagorean theorem. Pythagorean theorem, which says, in this case, that if I look at the length of my vector squared, that has to equal the sum of its two sides squared. So r squared has to equal x squared plus y squared. In geometry class, or in trigonometry, you may have heard this as a squared plus b squared equals c squared, where c is just the hypotenuse of the triangle. So I can use this to find the magnitude of my vector. Magnitude just means the length of the vector. So the magnitude of my vector, which I'm going to write as r. Now note, when I wrote r as a vector before, I wrote it as r with an arrow on top. That's a vector. That means I need the magnitude and the direction. If I want just the magnitude, I just leave the arrow on. No arrow means it's not a vector, it's just a number here. Number with some units, perhaps. R, I can get by taking the square root of both sides. So that's going to be the square root of x squared plus y squared. And in this particular example, that would be the square root of 3 meters squared. I got to put my units in here. Plus 1 meter squared. Which you can work out easily enough. This is just going to be equal to the square root of 10 meters. But the main thing we want to take away is this general formula, which we can use to figure out the magnitude, the length of any vector. We just get that by using the Pythagorean theorem. So magnitude is not the only thing we need. We need magnitude and a direction to define our vector. And our direction we can write as in terms of an angle. So I can say that my vector r is a distance blah blah meters. Let's say I'm making an angle up here. Let's say at a 30-degree angle above the x-axis. So if this is my x-axis, the angle from that axis tells me the direction that the vector points. All I need to do to specify the direction is just tell me what angle the vector is pointing at. There's a lot of different ways we can specify the direction. If we're in component form, the direction's specified automatically, because I know you go so far in the x direction and then some other distance in the y direction. If you want to write the direction explicitly, you can do it in terms of an angle. There are other ways to do it. If we're talking about directions on a map, you could say north, south, east, west. But for now, let's just focus on angles. How do I find that angle? Well, again, the answer is going to come from trigonometry. So you may remember from trigonometry a formula, or not a formula, but a mnemonic called SOHCAHTOA, which related the sines, cosines, and tangents of angles to different sides of the triangle. So the SO meant that the sine was equal to the opposite side of the hypotenuse. So that would be saying that the sine of this angle would be equal to the opposite side, which is y, divided by the hypotenuse, which was the r. Similarly, the ka would be equal to the adjacent side to this angle, in this case, the x distance, divided by the hypotenuse, which was again r. And the tangent, the TOA, was equal to the opposite side, which was y, divided by the adjacent side, which was x. We're going to use the tangent to find our angle. So we would say that the tangent of that angle, the tangent of theta, the angle tells me my direction for the vector, is equal to the opposite side, which we said was y, divided by x, the adjacent side. Tangent is opposite over the adjacent side. So we can use SOHCAHTOA to figure out the direction. And now, once we do that, we have a way to determine our magnitude and our direction from the components of the vector.